Back to the recording then. So time-varying predictors, the idea of looking at relationships within persons of predictors that are measured repeatedly with outcomes that are measured repeatedly. So either way, if we are starting from a within-person growth model or a within-person fluctuation model, from this point forward, time is not part of the story. I am assuming that you would have already modeled whatever effects of time that you need in terms of fixed slopes, random slopes, residual correlations over time, and whatnot, because at this point then time is irrelevant. So the residuals are relative to whatever growth trajectory you've already put in the data. If it's fluctuation, you may not need one, but either way, it would look like this. And what makes this so complicated is that all time-varying predictors, I would say all, most of them, except for balanced time, are going to have both between-person information as part of them and within-person information. And our job is to figure out how to separate them, how many different types of between-person information are there, and how they might relate to other outcomes. So this part of the story, to start with, is focusing in the context of a fluctuation model. So the daily diary kinds of things where you're not expecting systematic change. You're just interested in how people vary relative to their own mean levels. Later this afternoon, assuming we have the strength to make it there, we will add the change component to the story. So what would time-varying predictors look like if they also change over time? That's what can make it more complicated. So time-varying predictors usually carry at least two kinds of effects because they are really two different predictor variables in one. So if I ask you about your stress every day, it is true that some days are worse than others, and I would expect that that represents within-person variation in stress, deviations from one's own usual level. But it's also the case that some people are going to report more stress on average than other people. Now, I'm not going to argue about whether it's real stress or perceived. That's the, sort of the measurement issues aside. But there is a commonality in the responses that people give for predictors as well as outcomes. And in the same way that the first thing we want to do for an outcome is figure out how much of its variance is cross-sectional versus longitudinal, we do the same thing. So any variable in your data set that you intend to put in a model, I would recommend estimating an intra-class correlation for it to start with. So treat it as an outcome, just so you can see how much of its variation is in each kind. Because each source of variation is a logical prerequisite for it showing a relationship at that level. So if my intra-class correlation for a predictor is greater than 0, that means it has at least some between-person mean variation, and that between-person variation in a predictor has a chance to relate to between-person mean variation in an outcome. Likewise, if the predictor's intra-class correlation is less than 1, it has at least some within-person fluctuation to it, and that within-person fluctuation could predict the same fluctuation in an outcome. So knowing how much variance is of each kind is a useful step descriptively, but it then also dictates what's logically going to be possible. The relationships that one may end up with may be in the same direction across levels, or it can be in different directions. So if I think about the relationship between stress and health, it may be the case that people who have higher chronic stress have worse health outcomes on average relative to other people. And it may be the case that if I have more stress than I'm used to, that I feel worse than I usually do. Both of those things have a negative relationship between stress and well-being. It can be the case, though, that the relationships are in the opposite directions. So if I think about how exercise relates to blood pressure is often used as an index of fitness or health, such that people who are in better shape have lower blood pressure. So people who tend to exercise more have lower blood pressure, but when you're actually exercising, your blood pressure is higher than when you're not. So there's an opposite relationship because what blood pressure means is different at each level. And so for that reason, we would expect different relationships between persons than within persons, but also because these are all slopes that are unstandardized. And so the only Hey now. We're not done yet, Mr. Beamer. There you go. The only situation in which you would expect the same relationship at each level is if both variables had the same total variance, the same interclass correlation, and the same relationship. And that's not likely. So we will see that between-person slopes are going to be different than within-person slopes the vast majority of the time. So in terms of what kind of information you can get out of a model that includes a time-varying predictor, there's 3 different things one might want to know. I'm going to start with the first 2. The third is grayed out, and we'll get to that one a little bit later. So one way that a predictor and an outcome can relate to each other is between persons at level 2. If people are higher than other people on X, do they also tend to be higher than other people on Y? If so, then we would expect that the between-person variation within the time-varying predictor would account for random intercept variance at level 2 for my outcome. Also, separately, if I have a higher value of my predictor today than usual, is my outcome different than usual today as well? And so that would be an example of a concurrent relationship. It could also be if my predictor is higher today, is my outcome higher than usual tomorrow? You can have lagged relationships. So the time scale is completely up to you. But the key idea is the reference point is than usual. And if so, we would expect that that relationship would account for residual variance at level 1 in the outcome. So here is what not to do. Do I have everyone's attention? The espresso's on board, we're ready? Okay, if you take nothing else out of today, take this. Don't do this. This is the naive approach to fitting time-varying predictors. You think, well, it's a level 1 predictor, so I'll just put it in the level 1 model like this. I'll center it so that 0 means something, and here we go. The problem is that the relationship that you get, this slope that it conveys, is doing the work of 2 different variables. So the term that I use for this slope is I call it a smushed effect. That is a term that is in the index of my textbook. I'm trying to make smushed happen. Because to me, it's the easiest way to visualize the idea that you have a between-person slope and a within-person slope, and if you only allow one slope for both of them, they're smushed together. Other people have called this a conflated effect, which is a term I also like, a convergence effect, which is in the context of age differences and age changes. If you smush those together, it's age convergence. Another term is composite, but I don't like that one because it's not as descriptive. But the key idea is that if you have 2 different kinds of variation in your predictor and you only estimate one slope, you are assuming that that slope is the same across levels. And it's not going to be equally weighted. It's going to be differentially pushed toward the level 1 slope because in most cases there's a lot more information at level 1. You have way more occasions than you have persons, so the slope that you get will be close to what it should be for the within-person level 1 effect, but the level 2 effect will be misspecified. And so the rest of your level 2 model then is going to be incorrect as a consequence. So this is what not to do. Visually, the same model idea here. On the left-hand side, I have my original observed outcome at each time for each individual, and the model has partitioned its variance into these variance components, or piles as I call them. So we had residual variance at level 1, that represents within-person fluctuation around the person means, and then variance in those person means captured at level 2. Well, my time-varying predictor probably has these 2 sources of variance in it too, yet I've only allowed one fixed effect of it at both levels. And so that is the smushed effect that you end up with if you force it to be the same. So we don't want to do this. There are several different ways to fix it, and the way that you choose to fix it will dictate what your parameters then mean. So I'll show you the way that I personally prefer because it's the easiest not to screw up. Then I'll show you what is more common, and then we'll talk about how those same ideas translate or don't into the idea of latent variables within structural equation models or multi-level variants thereof. Okay, how are we doing so far? Good? All right. So then what we are going to do as our first option, this is the only option that you have if you use univariate software like Elmer, is to literally separate my time-varying predictor into the two variables that are embedded within it. So I am going to compute the mean across occasions of my predictor, and that's going to be a new level 2 predictor. And in the notation, I have labeled that as person mean x, and again, colors are going to be used for the same thing. So the level 2 effective x is going to be this green color. And we would center person mean x at a constant so that 0 means something the same as usual. The choices then come in as to what you do at level 1. So there is one idea that goes by a bunch of different names. In the context of cluster data, it's called group mean centering or cluster mean centering or centering within contexts. In longitudinal data, it's almost always called person mean centering. And the key idea here is that your level 1 predictor is not going to have a constant subtracted from it, it's going to have a variable subtracted from it instead. This is the way that I prefer to model longitudinal data. The alternative is to subtract a constant instead of a variable, and that will change what happens at level 2. So these choices only apply to the level 1 predictor, not the level 2 predictor. The level 2 predictor in both cases is going to be represented as an observed variable, the person mean, centered so that 0 means something. And this idea of grand mean centering, as it's often called, it doesn't necessarily have to be the grand mean. Everything that I have to say still applies if you leave it uncentered, if you center it at 4 or 2 or whatever. Because the key idea of this method that's second is that it's a constant that's being subtracted and not a variable. So here's my preferred approach, person mean centering. I take my original XTI, my time-varying predictor, and I compute first the mean for each person across their occasions. So that's X bar sub I. And then I subtract off a constant so that 0 means something. And that's going to be represented in my equations as PMX. So if I center at, say, the grand mean of this variable, then positive values of person mean x indicate that they have more than other people, more than average. Negative values mean that they have less than other people. At level 1 then, I take my original time-varying predictor and I subtract off the person mean that I just found up here, the uncentered version. So my new within person x predictor, what 0 means is that I am at my usual level. So a positive value of within person x means that I'm higher than usual at that occasion. A negative value means that I'm lower than usual because what usual is up here in green. So we are literally carving up my original time-varying predictor that had both between person mean differences and within person fluctuation into those pieces. And they will be completely uncorrelated. So we can stick each one in at its respective level. Okay, questions so far? No? All right. So here's what the model would look like then. And again, this is a fluctuation story. I've simplified it just to what we're focusing on, but you would have time or whatever else needs to be there, whatever covariates you're interested in. So the purple is level 1 within persons. And I have the box over here reminding us how that was constructed. And the green is level 2 between person. So because this new within person predictor only contains within person fluctuation around the mean, the slope that it has can only be the within person effect. So gamma 1O is the effect on y at that occasion for being 1 unit more than usual at that same occasion for the predictor. The other slope, gamma O1 at level 2, is the effect of having more x on average than other people. So the slope would tell you how much y changes on average for a unit change in person mean x relative to other people. So the key to keeping these things straight in your mind is to think about what more means in each variable. At level 2, it's more x on average than other people. At level 1, it's more x today than I usually have. So they each have their job to do at their respective levels, and they're completely unrelated to each other, which simplifies the interpretation. So this means that if I leave either of these things out of the model, the assumption that I'm making is that its slope would be 0, the same as we typically would do in any kind of linear model. So then graphically, what I've done is try to treat x in the same way that I'm treating y, except I'm doing it with observed variables instead of letting the model partition it. So the person mean x green square here is the observed variable analog to the random intercept on the y side. And the within person time specific deviation from that person mean, the purple box down here, is the observed variable analog to the level 1 residual variance for y. So I'm trying to carve up time varying x into between persons and within persons the same way that the model is doing for time varying y. And you might look at this and think, wait a minute, why is boxes on one side and circles on the other? That seems awfully arbitrary. And I totally agree with you. And solving that problem is one of the main motivations to switching to multi-level SEM, because that allows us to partition the variances of multiple variables at the same time. And so where we will eventually end up is the idea that x gets a random intercept and a residual in the same way that y gets a random intercept and a residual. But for now, within univariate software, we have to carve up x ourselves into observed variable predictors because the model only allows one outcome to be partitioned at a time. So then what might these slopes look like? Here are some hypothetical scenarios. So what this picture is showing is time varying stress on the x-axis. So not time, but stress at any given occasion. And severity, let's say a measure of some sort of health outcome where more is worse on the y-axis. And I have 3 different prototypical people here. My red person has a mean stress level of 4, my green person has a mean of 5, and blue has a mean of 6. And the slope through the means, the slope of this yellow line, is the between person slope. In this picture, it's 1, meaning that for every unit more stress on average than other people, severity on average goes up by 1. Each of these individual lines is designed to show the within person slope, which in this picture is 0. So this picture shows no impact of having more stress than usual on your severity. It doesn't matter. Now, if I were the researcher collecting longitudinal data and this is what I got, I would be very sad. Because this slope through the means is what I could have gotten by asking them one time. People with more stress have worse severity, the end. The opposite is the next picture. So camera 1, camera 2. Now, if this were my result, I'd be much happier because now I have a story to tell. In this case, there is no between person slope. The slope of the yellow line through the means is 0, but there is a within person slope of 1. So this picture is saying that it doesn't matter how much stress you have on average, but if you have more stress than you usually do, for every unit more stress, y at that same occasion goes up by 1. So it's all about the relative level of stress and not about the absolute level that you're used to. You can have both. So this picture shows a positive slope both between persons at level 2, such that for every unit more stress on average, severity on average goes up by 2, so the slope of the yellow line is 2, and the slope of the individual lines for the within-person effect is 1. So this would be a case where we definitely would not want to smush the two slopes together. Here and here, same deal. Okay, how are we doing? Thumbs? Questions? Okay, pausing to drink my coffee. So I have a little example for you, and then we'll walk through a more detailed one later. This is a true story. So I had a friend / colleague in graduate school who was in clinical psychology, and she liked to study positive psychology, things like coping and resilience and forgiveness and stuff like that. And she walked into her dissertation proposal meeting with an idea for a design where her husband was a dermatologist, and he had access to a special population of patients who had psoriasis, which is a skin condition that is thought to be exacerbated by stress and other kinds of environmental factors. So she was going to have people fill out questionnaires about their psoriasis, as well as questionnaires about their levels of perceived stress and coping and forgiveness and all these things, and she was going to have this nice cross-sectional study. She walked out of her dissertation proposal meeting with her committee having added a second longitudinal component to it. Because the novel question to be asked, according to them, was not just, is stress related to severity, but is it the case, like, if I feel more stressed than I usually do, does that show up in my skin later on? Like, is there more of a within-person relationship which gets you a little bit closer to a causal inference than just having between-person differences? Definitely not causal, but a little over on the spectrum. So they added a second component to her study. I actually helped collect this data. So this is back when I was stuffing packets into envelopes and mailing them out to people, and they mailed the packets back, and I had to enter the data into a spreadsheet, that whole thing. Dating myself, but this is how we used to do research in the olden days. And we had 8 weekly measures of stress and a few other outcomes, but the key one was psoriasis severity. And this is a plot of the individual trajectories that we ended up with. So the heavy black line is the mean over time. And on average, these patients are not getting better, which is to be expected because this is not a treatment study. They are already receiving some kind of treatment. This is just an observational design asking them questions. So in terms of what I would do for an analysis plan, first thing I want to know is intra-class correlations for stress and severity. How much variability do we have at each level? I would then want to assess the patterns of variance and covariance in severity as my outcome over time, and then eventually try to predict whether or not there is a lagged effect of how stress relates to severity concurrently at lag 0, as well as 1 week later, potentially 2 weeks later, and so forth. So step 1 then, intra-class correlations. So to remind you what the model would look like to get that, it's an empty model that has only a fixed intercept in the model for the means, only a random intercept for level 2 variation, and then the level 1 residual. The intra-class correlation is the proportion of total variance between plus within and the denominator that is due to between-person differences. And here's what I found. Severity had an intra-class correlation of 0.83. So what does that mean? Anyone want to put that in a sentence for me, if you're feeling brave? 83% of all of the total variation is because some people have worse severity than others. The way that I interpret that is that their longitudinal design is an 83% waste of time, because she would have already had cross-sectional differences from the study that she proposed. So right off the bat, I know that there's only 17% of this variable that could possibly be related to having more stress than usual. I can still try. I just know that it's not going to be optimal. Stress, on the other hand, is about half and half. So half of the variance in stress is because some people are more stressed out all the time. Half of it is because of which week is which. And after going through a long series of models, this is one of the examples in my longitudinal class, I settled on a model for the variance and covariance in severity over time that has a random intercept at level 2 plus a residual correlation structure that follows a Toeplitz pattern. So what I have here is the correlation matrix among the level 1 residuals across time, and that's why we have ones on the diagonal, because it's a correlation matrix. But if you look at the correlation between the first occasion and the second, it's 0.5. Second and third is 0.5. Third and fourth is 0.5. So if you look at the off-diagonal bands, all occasions that are 1 unit in time apart was estimated to be correlated at 0.5. And then 2 units in time apart is estimated at a correlation of 0.36. 3 units in time apart is 0.11. And after that, we didn't need any more. This is an example of a structure that is not readily available in most packages, but it is in SAS. And so this is what I ended up using for these data. So it looks like where your severity was last time is related, 2 times ago is related, 3 times ago is only slightly related. Then we get into the inclusion of time-varying stress. So this is the model that I ended up with, where I have within-person stress at the same occasion, so L0 means lag 0 concurrently, and then at the occasion previous. So to be able to fit this model, you have to lag your data so that the stress from the row before it is in the same row as the outcome. And every software package has ways to do that without you having to do it manually, fortunately. So I have 2 within-person effects, 1 between-person effect in this model. So if we walk through what's going to happen in terms of the fixed effects, gamma 0, 0 is my fixed intercept. That is going to tell me the expected level of severity at the 0 values of my predictors, just like an intercept typically is. In this context, what that means is for somebody who has an average stress rating of 2, because that's where I centered it, when they have a 2 currently, because that's when within-person stress at lag 0 is when they're at their mean, and when they were at their mean the last week as well. So that's my reference point. Then gamma 01 is the effect of having more stress than other people. Gamma 10 and 20 are the within-person effects of how does severity change currently and next week based on your levels of within-person stress, so relative to your own mean levels. So because I have carved these variables up into their level 2 between-person piece for the person mean and their level 1 within-person piece, I can directly interpret their slopes as between versus within. So here's what I found. This is a plot illustrating the findings where the x-axis is relative stress. So the middle is when you're at your own average. And then I had relatively low and high values, so plus or minus 1 standard deviation on the within-person variable. And then the separate lines are for different levels of overall stress. And most of the story here is carried by the level 2 effective stress. So the difference between these lines vertically is the idea of between-person stress predicting between-person severity. People with higher overall mean stress have higher overall mean severity. The lag 0 effect was not significant, but the lag 1 effect was. Very tiny, given the scale of these variables, but still notable. So 0.06 is the slope of each of these lines. So for every additional unit more stress than usual, your severity the next week goes up by 0.06. Yes?
I was wondering if all of the programs you showed us can handle this lag 1 variables equally well. Because, well, lag 1 for 8 weeks is okay, so we use 1 data point.
Yes, you do.
But if we then, for instance, are interested really in lag 2 and 3, then we kind of miss a lot of data, and I was wondering if this is possible in all programs or, yeah.
Because the lagged variables are observed variables that we created, you can do this in any program. But yes, in the traditional univariate multi-level approach, you would lose all of the occasions that don't have a corresponding lagged predictor. So yeah, if I wanted to do lag 3, I'd have to start at time 4 with respect to severity, because then I'd have the first week predicting that. So that is the downside. It is more frequently the case that these sorts of lagged relationships are looked at within a structural equation modeling framework so that you don't have to lose those earlier occasions, and also because people want to do this cross-lag thing. Like, is it stress that drives severity, or is it severity that drives stress? And they want to be able to do both at the same time. In this case, we had a directional hypothesis only, and I also have a personal belief that in order for a lagged effect to be valid and useful, that you should control for the concurrent. This is something that other people would disagree with, but this is my opinion. Because if you really want to tell me that it's last week's stress that matters, I want you to show that it contributes above and beyond this week. In the cross-lag models, the concurrent relationship is usually modeled as a covariance instead, such that you're not actually controlling for it. You're just letting it be there among the residuals. So this can be done in every way. It has disadvantages in the univariate MLM framework that can be overcome switching to an SEM framework. But then you lose the ability to have residual maximum likelihood and denominator degrees of freedom for small samples. So, yeah, you can't win everything, right? You can't have it all at once is sort of the bottom line. Okay, and here's code of how you would do this in all the packages I know how to use, and here's Elmer in the middle. So it looks very much similar to what we did yesterday. I have a note, though, that the R correlation structure that I had for the outcome is not possible within Elmer. It could be done in GLS if you built it in as a user-defined function, but I haven't figured out how to do that yet. Whereas in SAS and Stata, you can do those specific correlation structures for the residuals. So, other questions on the idea here? No. Okay, let me see. All right. So I like this approach because you know what you're going to get out of your predictors. If a predictor only has within-person information, it can only have a within-person slope. If it only has person mean variation that's between persons, you can only have a between-person slope. And if you leave out either one, you're assuming it's 0. Next, I want to show you one of the alternatives that is arguably more common. And what's going to happen is that we're going to switch how we define the level 1 predictor, but yet it's the level 2 fixed effect that changes its interpretation. Dun, dun, dun. So other questions or comments before we head in that direction? Okie dokie. Away we go. So what we have so far then, person mean centering can directly give us the level 2 between person slope. That describes the relationship among the person mean of X with the person mean of Y. And this does not control for the actual value of the time-varying predictor each occasion. The level 1 within person effect then is the idea of more than usual. So if I'm higher than usual on X, am I higher than usual on Y? And than usual is the reference point. So within person is capturing the relative changes in X, not the absolute changes. Here's the next piece of the puzzle that we haven't talked about yet. What person mean centering parameters that you end up with for the between and within slopes do not tell you directly is something that's called a level 2 contextual effect. So is this a familiar term yet? No? Okay, well, then let me tell you all about it. In longitudinal data, this is confusing. In clustered data, it makes a lot more sense. So you can think about the contextual effect in 2 different ways. One of the ways is easier than the other. Mathematically, the contextual effect tells you the difference of the between slope minus the within slope. So it is literally the difference in those 2 sizes of relationships is the contextual effect. I prefer to think of it that way in most cases. Alternatively, it is the effect of the person mean after controlling for the original value of the time-varying predictor at that occasion. So it is the extra contribution of the mean above and beyond the full level 1 predictor, not just the relative level 1 predictor. And we can get this additional slope in one of two ways. We could stick to our person mean-centered model that I prefer and literally ask for the difference in slopes as a linear combination. So I have listed here all of the packages that I know how to do this in. Every software package has a way to let it do math on the coefficients, and you can get the slope difference as an estimate, get a standard error for it, get a p-value for it. Alternatively, you can get the same level 2 contextual effect by switching how you define the level 1 predictor by centering at a constant rather than a variable. And it doesn't matter what constant you pick, it could just be 0 and leave it uncentered. Nothing changes in terms of the interpretation in terms of what I'm talking about. So why do we end up with two different level 2 effects based on how we set up the level 1 model is tricky to understand, but to be able to explain it, I'm going to go back to regression.
One question before.
Yes, please.
Why do we want to know if the slope is equal?
Haha. In longitudinal data, we don't, usually. Where this is relevant is in clustered data. The contextual effect tells you what is the effect of the group after controlling for the individual. So for instance, if I have something like free and reduced lunch as an individual level variable, whether or not a child gets free and reduced lunch is often used as a proxy for a socioeconomic status, for better or worse. And I might think that children who qualify for free lunch are disadvantaged and that they have lower academic outcomes. I know that to be true, at least in one data set that I have. So the contextual effect would say, after controlling for a child's lunch status, what is the incremental contribution of how many kids at that school get free lunch? After controlling for the individual, what is the contribution of the context? That's where the term comes from, as a contextual effect. And in clustered data, that's often what people want to know, is like, what does your environment do to you above and beyond your own characteristics? In longitudinal data, it makes less sense because occasions are not things the way that people are things. So like after I control for this occasion, it's like, why do I need to do that? So I would happily have skipped this entire section of the story if it weren't for one problem. Against your will, depending on how you set up your model in M+ or Levon, you will get contextual effects instead of between effects in some cases. You cannot get around it. So I have to explain what's a between effect and what's a contextual effect. That way, when you get your output, you'll know which kind you have. And you can convert from one to the other, but they mean very different things. Okay. For group data, it makes a lot more sense. It just doesn't make as much sense for longitudinal, but we're going to be stuck with it, unfortunately, because of the way that the software operates on the observed variables. So how this works then, let me go back for a moment to regular old regression. Remember those days when all we had was one pile of variance and one subscript and everything was straightforward? So if I have just a regular old regression model and I have two predictors in it, if the predictors are unrelated to each other, then each of their slopes carries the full bivariate association between that predictor and the outcome. But if the predictors are correlated, what their slopes are when the predictors are together are going to be different than what their slopes are when the predictors are not together. It's the idea of collinearity. And the way that we would talk about it is in the model where they're together, beta 1 gives me the unique effect of x1 after controlling for x2. Likewise, beta 2 gives me the unique effect of x2 after controlling for x1. And those unique effects are not the same as the original correlations between x and y, because they're fighting against each other with their shared variance. The same thing is going to happen in our models once we switch to a level 1 predictor that has all of its variation in it. So here's a comparison of what it would look like then to have two different versions of this level 1 predictor. At level 2, it's going to be the same. So let's say that I have 2 rows of data from one person, and then below the line are 2 rows of data from a different person. And the first person had a 2 and a 4 for their occasions, which gives them a person mean of 3. The second person had a 6 and an 8 for their occasions, which gives them a mean of 7. So either way, at level 2, I'm going to put in the person mean of this variable, center it so that 0 means something. So I might pick 5 as the middle of this distribution. So minus 2 goes in for the first person, 2 goes in for the second. Cool. Now where we started over here is this column that's labeled person mean centering. We took the original time-varying predictor, so the 2 and the 4, minus the person's mean, so the 3, and I end up with within person deviations from the mean of minus 1 and 1 for the first person as well as for the second. So this column right here only contains relative information. Where are you now relative to your mean? So it's only level 1 within person information. All of the level 2 between person information is over here. But if I use grand mean centering or centering at a constant more generally, then I'm just subtracting the same value. This column contains both relative information and absolute information. Subtracting a constant leaves all of the level 2 information still in that variable. So the end result is that the effect of this variable and the effect of the person mean are going to differ when they're put together because they share variance. The person mean holds between person information, but so does this column. And it's going to change what the coefficients mean if you put in this column at level 1 rather than the person mean centered column. Okay, how are we doing? This is a lot. Remember, that's my caveat. This is a lot. If you're sitting there thinking this is a lot, you're correct. So here's what's going to happen. At level 1, I have changed my notation to be time varying x, meaning this version of the variable that's centered at a constant. It still has both level 2 person mean between person variation as well as level 1 within person relative variation. So it has 2 different piles of variance embedded in this predictor. At level 2, we have the same person mean x that we had before, but it's in a different color because it's going to mean something different. It only has level 2 variation. So think about this in terms of collinearity among predictors. Okay? They're correlated. Both of these predictors have level 2 person mean variation in them. So when I put them both into the same model and they compete against each other, what does time varying x have that's unique to it that's not in this other variable? What's in it that's unique? What kind of information? Any guesses? What does the purple box have that the teal box does not? The level 1 variance. So when you put these two together and they fight against each other, what you end up with for the slope at level 1 is the same within person slope we had before. It's the same because it represents the unique effect of that level 1 predictor after controlling for the level 2 person mean. And that unique effect is the level 1 effect. The idea of the change in y at that occasion for having more x than usual for each unit. Now the other one, you would think that because it only has level 2 between person variation, that that's the kind of slope it should have. But that's not what happens. It becomes the contextual effect. because it is also controlling for the overlap that it has with time-varying x. So part of the between effect is already embedded in this purple level 1 predictor. The person mean predictor steps up to fill in the difference as to what it would get to go to the full between level 2 effect that it needs. Graphically, it looks like this. So time-varying x still has between and within variance in it, so the slope that it gets is operating in both places. The level 2 person mean steps up to fill in the difference as to what it would be to get to the full between person effect. It carries the contextual effect. I have a picture, another one that might help. I keep throwing pictures at you. One of them's got to stick, right? Eventually. So this is a similar picture to what we saw before, where time-varying stress is on the x-axis, time-varying severity is on the y-axis. The lines are depictions for people with different average levels of stress. So if we map the parameters that we saw out of the person mean-centered model, the slope of the yellow line through the person means is 2. So that means that for every unit more stress you have on average than other people, your severity goes up by 2. The slope of the individual lines shows the within person effect. For every unit more stress you have than your mean, your severity goes up by 0.5 in this picture. The new thing that I'm trying to explain what it means is the slope, if you will, of this vertical line. It's the idea that after controlling for the absolute amount of time-varying stress, so like conditional on a stress of 5 here, it is the incremental contribution of the person mean. So the difference is 1.5. For every additional unit mean stress you have, severity goes up by 1.5 after controlling for your stress at that occasion. So the contextual effect is given by the vertical line here. The between person effect is given by the slope of the yellow line through the means. The within person effect is given by the slope of the individual lines, which shows up in the model the same either way. Whose head hurts looking at this? Can I get a show of hands? No one's willing to admit it. My head hurts looking at this. Here's an easier way to say it. The between slope is more positive than the within slope by 1.5, the end. Is that better? Not maybe? It's easier to say, but then it's like, well, what does that mean? And the reason that I have to explain this, as much as I do not want to, is because sometimes you will get contextual effects at level 2, sometimes you will get between effects at level 2, and sometimes you'll get a mixture of both, depending on how you set up the model. All right, the good news is that either way, you can get back to all 4 fixed effects. So here's some algebra that shows the relationship, but the point of the story I want to make is that if you use person mean centering, what you get directly is within and between. Contextual is the difference. If you use constant centering instead, what you get directly is within and contextual, but you can add them together to get to the between. As long as you only have a random intercept, this equivalency holds. If you don't have only a random intercept, if you add a random slope, so a U1 term here, then the equivalency does not hold. Because the random slope multiplies just the within part of the variable if you use person mean centering, and it multiplies the whole variable if you don't. So what ends up happening if you use a random slope on a constant centered predictor is that the random slope is smushed in the same way that the fixed slope can be smushed. And that causes problems with respect to the model for the variance and the implied heterogeneity across the predictors. So we prefer the idea of a person mean centered slope to prevent that problem. So let me go back to this right here. This within person slope right here is only fixed. What do you think it would mean if I added a random slope? Conceptually, could I have a random slope of my level 1 predictor here? Just like I got a U here, could I put one here? Could. What would it mean if I had, say, severity as my outcome and stress as my predictor? A random slope for the effect of stress would mean what? Random slopes yesterday were each person needs their own rate of change, right? Over time. So random slopes today would mean each person needs their own rate of change over stress. So a research question that would lend itself to the addition of a random slope would be something like, are some people better than others at handling stress? Or if I handle stress well, that could mean that more stress than usual does not affect the rest of my life. That I don't have a slope, basically. My slope is flat. Whereas for some people who don't handle stress well, then more stress leads to more badness in the rest of their life. So random slopes carry us forward for other variables besides time. And if you're interested in that, then you don't want to do it this way. You want to do person mean centering instead. The idea of a buffering hypothesis, that people who are better at coping are better able to handle stress. That would be what's known as a cross-level interaction, for instance, with coping here, such that the relationship between within-person stress and severity is moderated by how forgiving you are, how good at coping you are, other sorts of positive psychology skills that you have. Or it could be exacerbated. Maybe somebody who has a very poor social support, then the relationship between stress and severity is stronger if you don't have someone to lean on than if you do. Those are all examples of the idea of a random slope for how people handle stress differently. That random slope variance could be explained by person characteristics such as their personality, their coping skills, their social support, and things like that that are constant over time. So some of you are nodding. Is this giving you ideas for things to look at, maybe? Any examples you want to share we can talk about? I know I'll be talking with some of you tomorrow about your data, but if you want to jump ahead, get some free consulting now. You know, I charge money for this usually. It's very easy to get lost in the details. And so what I want to be able to do is to try to have you think about, like, how would this apply? Like, how would this work in terms of hypotheses and data? That's all I'm going for. No. Okay, fair enough. What do I have next? Categorical predictors and then summary. Yeah, okay. Let me skip a couple slides here and do this. So I had a chance to write a review article for the annual review of psychology last year. And I had a lot of fun writing this. It was with the former graduate students. We sort of wrote the article, and then we're trying to figure out, like, how do we pitch what we've written? And we came up with the idea of catching up with the TV show. So we named the article Catching Up on Multi-Level Modeling, and we talked about, like, in season 1 this happened, in season 2 this happened, in season 3 this happened, and I think it worked out. At least it was fun, more fun than writing an article. But this is one of the tables in the article that best illustrates why I vastly prefer person mean centering, or centering at a variable as opposed to a constant. So the notation that we used in that article was W for the within level and B for the between level in this thing. Is this too small? I can make it bigger. It's good. Oh, well, you got it in front of you, right? So you can zoom in your faces as much as you want to. This is just an example, by the way, that your subscripts don't have to be IJ. Whoever made that rule needs to be drug out and shot, because IJ does not work for most situations. J does not start with anything. So you can pick whichever letters you want that actually make sense. The only letter that I avoid is O, because it looks like 0, and then it gets confusing. So I picked within for level 1 and between for level 2, because that's what we call it. So here are the two different versions of the model that we've talked about. The first section here is for variable-centered level 1, where I subtract the between-level mean. So this would be the person's mean in a longitudinal context. It would be the cluster's mean in a clustered context. So if I put in this level 1 person mean-centered variable, and I put it in all by itself without the other one, it carries the within effect. If I put it into the model with the person mean, it still carries the within effect. Likewise, if I put in the level 2 person mean, centered at a constant so that 0 means something, into the model all by itself, the second column here, it carries the between effect, and it still carries the between effect if I have the other one with it. And if I leave either out, I'm assuming that its slope is 0, the same as if you leave out any predictor in the history of the world. That's why I like this. You can't screw it up. You literally carve up the variable into the two kinds of variance it has, and each variance can only have that kind of relationship. Alternatively, constant-centered level 1 here, arguably more common. If I put in my level 1 predictor centered at a constant all by itself, I get a smushed effect. What I assume then about the level 2 between effect is that it's the same as within. It's one slope that has to do the work of two predictors. If I put in the level 2 person mean by itself without the corresponding level 1 term, it carries the between effect the same as it does in this model because it's the same variable. But if I put in the level 2 person mean with the constant-centered level 1 predictor, then it switches from smush to within, and at level 2 it switches from between to contextual. Keeping track of this is challenging enough if you only have main effects. But what about interaction terms? What if I wanted to look at how two level 1 variables interact with each other? I have to unsmush the interaction terms too. So keeping track of what everything means when things are in and out of the model is much more challenging if the level 1 predictor has been constant-centered than if you have carved up the variance into within and between yourself. So that's my sales pitch for why I prefer variable centering. All right. For categorical predictors, the same is true. So for instance, if stress was measured as yes or no, I had a stressor today. Person mean centering is still okay, but it's kind of weird. Because it's like you have a 0 and a 1, that already means something. If I person mean center and say I have stressors on half the days, then my values are minus 0.5 and plus 0.5, which can't even happen. And if that's part of an interaction term, then the conditional main effects are conditional on values that can't happen, and that's weird. But the same problem can occur. It's a smushed effect if all you do is put in that 0-1 categorical predictor. So you'd want to, at a minimum, put in the person mean and have that represent the level 2 variance. And I have a link here to a recent paper that I really like. It should be out in Psych Methods either later this year or next year. That's a tutorial on this. And I think they do a very good job of walking through all the different coding schemes that you might have and how you would interpret the level 1 and level 2 effects under those different predictor coding schemes. But it may be the case that the person mean doesn't make as much sense as other alternatives. So if I had something like stressors, I can have a stressor one day and not the next, right? And it can come back the following day, no problem. But let's say that I have something like a diagnosis that's eventually going to happen over a longer term study, say of dementia or something else that doesn't go away. It's not like, I'm fine, I'm diagnosed, and now I'm not fine anymore. It doesn't work like that. There is a trajectory slide that you're sort of on this way prior to that point. So people who are eventually going to be diagnosed look different before than people who are not. So if I had a variable like this, the way that I would represent its level 2 variation is not the proportion of occasions on which I'm diagnosed, but literally am I going to be or not. And that would allow me to estimate separate trajectories from the beginning of people who are on their way to diagnosis from those who are not. But then also at level 1, I can put in the when are you diagnosed variable so it creates like a step function so that I can look at the acute effects of before and after diagnosis in the people who are going to be diagnosed. Because I can't look at the effect of dementia in people who aren't going to have it. It's a constant for them. The same thing would be true for any other phenomenon where it doesn't go away. Like if it's a shift in state. That's very different than a transient thing where a person might make more sense. So there's not necessarily a single right answer in how you would think about categorical variables. In some cases, you might need to think about it as sort of kinds of people and create a coding scheme that takes that into consideration. So there's my sales pitch for that. All right. Yeah. Okay. Summary. There. Yes, please ask me your question.
Bringing you back to the categorical ones, can I?
Certainly.
Yeah, and if the categorical predictor is something that happened, so not like I have a paper and we have the meeting was face to face or not face to face. Done. Then it's already published, but spoiler, we did not center it, but yeah. But it's in M+ with this implicit centering when you put it on both levels.
Okay, so the implicit centering when you put it in both levels changes it. Because what I understand you to say is that you treated it as if it were an outcome. You estimated a random intercept variance and a residual variance for it, the implicit centering, otherwise known as latent centering. Yeah. Mm-hmm. So then it's not wrong.
Yeah, I'm happy to hear.
It's not wrong, no. That is the third option that we will get to after lunch. I see your faces and I'm paying attention. I know we're at the end of the attention span, but no, that the only way that might be wrong is if you didn't tell the program it were categorical, because you can't do that in ML currently, but you can do that in Bayes. So you would have to estimate basically a logistic model to predict that as an outcome since it's 0, 1. So you'd have a link on it. You wouldn't have a separate residual variance that's an estimated parameter for the within part. That's where it gets tricky. So did you do that?
Yeah, maybe another time. We will not steal others' time.
Okay. Yes, and I have a very long list of papers that I now know to be wrong because it was the best I knew how to do at the time, including one that won an award, by the way. I have an award-winning paper that I'm about 90% sure is wrong, but I've never actually done the analysis to prove it. So I can still sort of have hope in my head that it wasn't completely wrong, but we all do the best we can with the tools we have and the knowledge we have. All right. Would now be a good time to take a lunch break? Think maybe? Yeah? Yeah, I think so. So... yeah, then that will be the foreshadowing of where we will head this afternoon is the idea of latent centering, and we'll see an example of how the results compare across different ways using M+. So I will hit stop.